Imagine a supernova exploding. Bits and pieces of it are flying out at 10 million miles per second. Its light shines as bright as 100 billion suns that we can see for months from Earth, and a surprise element was flying out as well. The closest supernova to happen in hundreds of years was in 1987, over 30 years ago, and with 2 expected every century, they're way overdue. But that's not why that supernova was important. It was also the first and only explosion we ever managed to detect neutrinos from, the smallest of the fundamental particles and that surprise element I mentioned earlier. In some types of supernovae, 99% of the entire explosive energy is emitted in the form of neutrinos, providing an easy cooling mechanism for the star. Nowadays, neutrino detectors are poised and ready around the world to detect neutrinos from the next explosion. Some of these detectors are filled with the noble element argon at very, very cold temperatures at which it is a liquid. Liquid argon detectors are uniquely good at detecting a particular type of supernova neutrino, the electron neutrino, via inelastic collisions with the argon atom. So what can we do in the meantime, while we wait for the next explosion? Well, we can actually practice detecting them. With the SPND detector at Fermilab and the man-made neutrino beam pointing towards it, we can study electron-neutrino argon interactions. And this is where me and my PhD come in. So how does it work? The neutrinos in the beam are of different types and are all moving at different speeds and energies towards the detector. But our supernova neutrinos are of much lower energy than most of the neutrinos in the beam. So we must think of a trick. Some of the neutrinos in the beam are created by another type of particle called a muon, which transforms into the neutrino on its way down the beamline. If we then add pieces of concrete, for example, at the end of the beamline and make these muons stop, this will create the low-energy neutrinos we are looking for, because they will have very little energy to begin with from that stopped muon. So what do we have so far? We have our liquid argon neutrino detector, SPND, and we have found our fake supernova electron neutrinos within the beam. But what are we actually trying to measure? In particle physics, we use a quantity called the cross-section, which essentially describes how probable it is for one particle to interact with another, or in other words, just how much they like each other. It's as if the more probable the interaction between the neutrino and the argon atom, the larger the argon atom becomes to invite the neutrino to collide with it. This cross-section number has never been measured before for inelastic, low-energy electron-neutrino argon interactions, and this is what I hope to accomplish with my PhD and aid in the discovery of the next once-in-a-lifetime supernova explosion.